So the people who are here, right, thank you for showing up on a Friday. Um, we have two speakers this semester, like less than our usual three or four, because we want to be a little more hands-on. So we're going to see how this works out. Our first speaker today is Katie Mann, who's at Cornell. And she's giving us a big picture idea of sort of I think why we should care about orbit equivalences of pseudo-Anosov flows.
Great.
Yes.
Thanks very much. Thanks to all of you who are here, and thanks in advance to the people who are watching me in the future on the recording. So this is about a particular class of flows on three manifolds. So let me just start by talking about flows, right? A flow, right? Phi t is just, it's a one parameter family of diffeomorphisms. So for each t, I have a diffeomorphism from my manifold to itself. And right, flow, of course, just means that like phi t plus s, I think of this as being like a progression of something over time, right? Is what happens if I do something for time t, and then I do it again for time s. Right? A really nice class of examples comes from geodesic flow. So this is the special case. Let me just make some room here, where your manifold M happens to be the unit tangent bundle of another manifold, which I'll call N. This is some Riemannian manifold. And the picture for geodesic flow, right, is let me draw N as if it were like the round sphere. Here's N. Its unit tangent bundle is all the tangent vectors attached to it. And if I take a point x in the unit tangent bundle, that's a unit tangent vector. What geodesic flow at time t does to it is I look at the geodesic tangent to this. I travel along for distance t, or I flow at unit speed for time t. I end up at a new point, and I take the tangent vector there. And that is by definition phi t of x. And if you think about this a little bit, so what am I seeing here? I've honed in on a point and sort of drawn a picture that will tell you what the trajectory of the orbit of this point looks like as you vary time, right? But the other thing is you can fix a time and see where all the points go, and that gives you a diffeomorphism of your manifold. Okay, now when I do this example of geodesic flow on the round sphere, it is, I don't know, maybe not super interesting for dynamicists, right? So let's make some observations. N is the round sphere. Then all of my trajectories, all of my orbits are periodic. Meaning that there's some time at which you just come back to the initial point you started at. In fact, they're all periodic with literally the same period, right? If I take a perfectly round sphere, maybe like 2 pi or something. And these orbits are predictable. What I would call predictable in the following sense: if I start at a slightly different position, like, this tangent vector instead, which is nearby, it will follow a periodic trajectory of here exactly the same period, and where the trajectory is very close to the original one. Okay. Right, and you can even quantify like how little change leads to how little change in global behavior. Okay. Right, but the system as a whole is not predictable and not boring in that sense. What we have is global instability. Meaning, if I change it a little bit, like you could think of even just changing the metric on this topological sphere to something that's not the round sphere, but like an ellipse or something. If you've ever done Riemannian geometry and had to learn about geodesics on ellipses, like that is a hard problem. You get qualitatively very different behavior as soon as you do a little perturbation. You won't have all periodic orbits. You'll have things that go on forever. It's really hard to understand the whole system. Okay. So, you know, for instance, if you're a physicist or something, uh, then it's really, this is not the kind of system you want to study because you need to know everything exactly on the nose or else you don't know the behavior. Okay, by contrast, if I take a manifold of negative curvature, so I'm thinking all my manifolds are going to be closed, compact manifolds, but I can't really draw an honest to goodness piece of negative curvature on the board. So I'm going to draw just a chunk of like the pseudosphere, right? I've got this kind of bell shape that looks like negative curvature going on. If I think of geodesic flow on its unit tangent bundle, I have very different qualitative behavior, right? So I'll draw a cartoon. Here's a geodesic. Maybe it sort of goes out this end, it starts to loop around. If I start with a geodesic that's just very slightly off, pointing in a different direction, I'll get wildly different behavior, right? You can imagine even just from my cartoon of what negative curvature looks like, that this is going to head this way, go around the back, start looping. They diverge sort of if you lift it to the universal cover, they diverge at an exponential rate. So here for geodesic flow, on this manifold, the unit tangent bundle, orbits are not periodic. There are some may, if your manifold's compact, some will be periodic, some will be not. They are not predictable. They're maybe more what you would call chaotic, meaning that a small change in initial direction leads to a very different trajectory. But remarkably, you see global stability of the system. Okay, meaning that a small change to the whole system, like if I changed the metric a little bit, or if I even forgot that my manifold M happened to be the unit tangent bundle of something else. Instead, I just have this abstract flow and an abstract manifold. You know, it's generated by some vector field. I could just change my vector field a little bit and not, you know, pay attention to where it came from. What I'll get is a new flow that is qualitatively and actually quantitatively has the same type of global behavior. And so my next goal is to try and make that precise. But first, I'm going to tell you where this idea comes from. Okay. And this really was something studied by Anosov in the 60s, who showed that geodesic flow on manifolds of negative curvature has this stability property. And the phenomenon behind it is what we call an Anosov flow. Okay. So of course, Anosov did not call this Anosov flow, but this was sort of the key property that led to stability for geodesic flows. Okay, so here's definition. A flow on a manifold M is called Anosov if, well, the way to think about this is it's sort of like the analog of a matrix that looks like, you know, lambda 0, 0, 1 over lambda, that it's got eigenvalues that are bigger and less than 1. Okay. So what's happening here? Why is this like matrix something interesting to study, right? It has a fixed point. It has a direction that's expanded. It has a direction that's contracted, right? And if I take one of these other points, like the trajectory kind of goes along as I iterate in a predictable way. Okay. This kind of behavior is already kind of stable in the realm of linear maps, right? If I just change the entries of a matrix like this a tiny bit, it will still have eigenvalues that are 1 bigger than 1, 1 is less than 1. And the eigendirections might be different, right? I might not have the axes anymore, but I'll still see the same kind of picture. It'll have a contracted eigendirection and expanded eigendirection and look the same. Okay, maybe I'll be contracted at a slightly different rate or expanded at a slightly different rate, but the kind of cartoon picture I've drawn of this is the same. Okay, so that's kind of the baby inspiration for what we're now going to do in the flows setting. Okay, so back to my definition. A flow on a manifold is Anosov if there exists a continuous invariant splitting. So my flow is not a linear map, right? So I should look at its derivative and what it's doing to the tangent bundle of M, where I can talk about this. So there's a continuous invariant splitting of the tangent bundle of M into direction of the flow so X I think of as the generating vector field, or as like ddt of my flow phi t. Okay. Direct sum and direction that is contracted, which is called the strong stable direction. And then a third direction, or if my manifold has higher dimension, maybe it's a whole plane field, many directions that are uniformly contracted. Sorry, strong stable is contracted, strong unstable is expanded. So that's uniformly contracted. This one uniformly expanded. What do I mean by uniformly contracted, expanded? Let's make this precise. So explaining what I just wrote, for all tangent vectors, say in the contracted one, the following holds. Okay, just put whatever metric you want on your manifold that induces as a norm on the tangent vectors, right? I want to compare the norm of what flowing for phi t does to this tangent vector, right? So this is like the derivative of my map. What does it do to a tangent vector? If it's in the contracted direction, then its norm after flowing is up to some constant, so that it doesn't depend, that this property is not particularly sensitive to the metric you chose. So there exists C, K, positive constants. This is now, its length is now bounded above by e to the, oops, what do I want? A big negative thing to make it smaller, minus K T norm of V. All right, and this is for all t greater than 0. Okay, so that's a precise way to say that there's some uniform amount that vectors in the strong stable distribution get contracted. And a slick way to write the unstable version is also for all vectors in the expanded direction. You're expanded if in your past history you were closer together, right? So I could write literally the same thing, except at the end, I'm going to say for all t less than 0. Okay, and that's the definition of a Anosov flow. Okay, so what Anosov shows is that geodesic flow is Anosov, a negative curvature. On when M happens to be the unit tangent bundle of N is Anosov. Okay, and that's not the hard part. The hard part is that this kind of condition implies that you're stable under perturbation. So I'll give one version of this, which is easier to write down. It is C1 stable, meaning if I take my flow, phi t, and I take another flow that is C1 close, which just means the generating vector fields are close as like vector fields on your manifold, point-wise. Then it looks a lot like the original one. So in fact, it's exactly the same up to the two obvious little changes you could make. What are the two obvious little changes you could make? You could sort of change coordinates on your manifold, right? You could just conjugate the whole picture by some little homeomorphism or diffeomorphism and get a new flow that's nearby, just a little bit different. The other thing you could do, right, is you could slow down or speed up time a tiny bit, right? Instead of progressing at unit speed, you could say in this little region, I'm going to go at speed 1 plus epsilon. Okay. Those are the
Katie.
Oh, question, yeah.
Quick question in the chat. Are the C and the K in the norm contraction expansion the same for unstable and stable directions?
Yes. Yeah, you can take them to be the same. Because I mean, just take the one that's worse if you want. Here's a fact, actually, if you're on a compact manifold, there always exists some metric where you can take the C to be 1. So you don't need a C fudge factor. Okay. I guess what you might say, actually, let me reinterpret your question. You're maybe asking about the optimal possible C. Are they exactly the same in both directions? Not necessarily, but we just want there exists something that works, right? And the way I've written it down, it's sensitive to your notion of norm. Okay, but the existence of a C and a K, if you're on a compact manifold, is not sensitive to the notion of norm or the metric that you put. Okay, so where were we? I wanted to say, what does it mean to look the same? This is called being orbit equivalent. Then phi t are orbit equivalent. Okay. Meaning, this is the key definition, there exists a homeomorphism of your manifold, right, that takes orbits of one, trajectories, like whole trajectories of one, that takes the orbits of one to orbits of the other. That's orbits equivalence, which is one thing that we wanted to define today. So what is this thing? It says if you forget time, right, how fast things are moving, then the ways the orbits travel through your manifold look exactly the same. Up to h, which is just doing a change of coordinates. Okay. Okay, so this is very cool. Once you have a notion of stability like this, right, you can advertise your work to applied mathematicians and physicists by doing this pitch saying like, well, you can only ever measure something up to finitely much perturbation, right? We don't have exact instruments. I know what it looks like, even if I instead took something close by, says that this is like an object in the world you could help to study or something. That's not my motivation, but it's a sales pitch that works pretty well. What I like for motivation and why this gives us hope to understand these systems completely comes from an observation of Steve Smale. So Smale, in his 1966 ICM address, points out that when you have a notion of stability like this, two things close by in some sense are the same in some other sense, there's a hope to classify all possible examples all Anosov flows on compact manifolds, say, up to orbit equivalence. All right, and the classification would hopefully look like just by some discrete, numerical or algebraic invariance. The fact that a perturbation doesn't change your orbit's equivalence class means that this classification should be by something discrete. Okay, maybe you can have a list of all possible ones. There's going to be at most countably many Anosov flows on any given manifold, and there's only countably many compact manifolds, so like total. We could list them all if we were really good. And he names as a particular problem that we should try and do this. Now, he has a very good conjectural picture for the sort of iterated version that's more like iterating a matrix, Anosov diffeomorphisms, but not really a good conjectural picture written down as like what invariants these should be to pick out, right? Specifically, though, as a first case, there is one kind of good simplifying assumption to make if you wanted to start trying to make a classification of all possible Anosov flows, which is to look at ones that are transitive. Okay, so let me tell you why and what that means. Classify transitive Anosov flows. Okay. Transitive means that there is a dense trajectory. Some orbit is dense. Okay, so you start somewhere and you go everywhere. In the non-transitive case, you might have sources and sinks, and there's a theory about how you could cut up your manifold into sort of basic pieces that capture this behavior. There's parts that don't interact with other parts. That gets complicated, but if you understood transitive flows, hopefully you would understand the building blocks that make other examples. All right. Okay, so that's in the 60s. We should look for all examples of this remarkable stable behavior. What do they all possibly look like? And at that point, very few were known. Geodesic flows and negative curvature, and ones that come from kind of an algebraic construction where you take like a linear matrix with distinct eigenvalues, contracting, expanding, and you build like a mapping torus of that map and flow along. This is a standard construction called a suspension. Okay, I won't do this as another example. I think Mauro will do this in some of his intro stuff. But that was it. That was the full complete list. And weirdly, on high dimensional manifolds, that's close to still the complete list of examples that we know. There's one trick to produce new examples. But in dimension 3, starting in the late 70s and 80s, a whole zoo of new examples of Anosov flows were produced. Right. So starting in the 70s, 80s, and actually this is still a very active program today, building crazy examples of Anosov flows on manifolds. Many new examples in dimension 3. All right. And these were obtained by various kind of cut and paste and surgery constructions. So for anyone who's a fan in the audience of three-dimensional geometry and topology, you might have learned that there's good ways to, cut and re-glue three manifolds to make new ones, right? Even these kind of canonical things, like you get a three manifold, you think of it's like torus or JSJ decomposition. We talk about three manifolds in terms of cut and paste. Well, there are ways. This started with examples of Handel and Thurston, and then Sue Goodman, David Fried, etc., that exploited this, saying if you could cut up and open your manifold in a way you knew. So let's imagine that you had a surface that was completely transverse to the flow, right? So here's my manifold. That's three-dimensional, even though it just looks like a blob. Maybe in here, I had something that separated it and was completely transverse to the flow. Okay, or, I don't know, maybe my manifold, maybe it doesn't separate, but it cuts one part from the other, something like this. All right, this is a very, very cartooned version. I could cut along something that is transverse to the flow. All right, so now I have a new thing with partially defined flows, right? That goes out one part and comes in another. If I re-glue this back to itself in a different way, I can change the topology of the manifold, right? But I'll still have a flow because, going out, I'm just supposed to keep going and come in wherever I re-glued this. I'll know the trajectory continues. Maybe this point gets glued to that point. No problem. Exit here, keep going there. It's a flow, right? And okay, so you can write down such a thing, and then you have to prove that if you're extremely clever and do it exactly the right way, the resulting flow you get is still Anosov. So there's a library of techniques that do these cutting along surfaces which are transverse or not quite transverse or blowing up, squishing back down. All of them are rich and interesting and difficult that let you change the manifold to one that was not a previously known example, and yet it still supports an Anosov flow. Okay, so this is saying that the classification problem on three manifolds is starting to look interesting and tricky. If we want to list all examples, that list is going to be long. Okay, but it gets actually even more interesting. Starting in the 2000s up until last year, and probably still going on, people come up with new recipes. We discovered ways to do this where you didn't change the manifold, you changed the flow. So examples of many Anosov flows on the same manifold. So for instance, Béguin, Bonatti, and you gave examples where if you give them a number, so for any number n, they can build you a manifold that has at least n distinct Anosov flows up to orbit equivalence. So at least n distinct orbit equivalence classes of Anosov flows. Jonathan Bowden and I gave another construction of this more recently that lets you have the manifolds be hyperbolic. So if you are interested in hyperbolic geometry, or you want you think that's sort of a simple or generic case of manifold, great. A different construction, but you can also take M to be hyperbolic if you like. Bears have lots of tori in them. Adam Clay and Tali Pinsky gave a third totally different construction just a year or two ago. All right, so there's lots of ways to get examples of manifolds with huge numbers of flows, but still open. And this is something that we would all like to solve. Does there exist a compact three-manifold with infinitely many orbit equivalence classes of Anosov flows. If I had to put a bet on what the answer was, I would say no. I'm on team rigidity. There's a finiteness statement. But there, I know people who are on the other team, whether they say so publicly or not. And so that's one thing, hoping to get invariants that describe these, we hope to address that problem. How crazy is the land of Anosov flows on three manifolds? Okay, so let me just recap what this classification problem therefore should look like. There's kind of two parts. Okay, one is trying to understand, let's just do on three manifolds, because this is where we have it's already the Wild West out there. The classification problem now becomes like step one, understand which three manifolds to have any Anosov flows. Okay. We have lots and lots of different examples, but we also have examples of three manifolds that do not. So it's been known for a long time that, say, like the three torus Euclidean three manifolds cannot admit Anosov flows. A necessary condition, which was proved by Plant and Thurston, is that the fundamental group of your manifold has to have exponential growth, whatever that means. But it rules out various geometries. Okay. But this question, so it's got a lot of attention and we can say a lot, but it's not totally resolved, right? And then there's a second part dealing with this kind of zoo, which is for some fixed three manifold, find invariants okay, that distinguish all the different flows on that particular manifold. Right? Solve the classification problem on a given manifold. Okay. Okay, and this having received lots of attention, what I'm talking about today and what the subject is of this little module is this second one. Okay, so I'm going to give you now one invariant, just like a thing that you could write down. Oh, this is getting very chalky. That's better. All right. If I have a manifold, I have a flow on it, right? The trajectories make, one-dimensional trajectories in my manifold. One thing I could just do is record all the periodic ones, right? These are going to be a bunch of loops. So a flow gives me a collection of loops in my manifold. I could think of these algebraically as just like free homotopy classes of loops, of circles sitting inside the manifold. And I could write these down. All right. So here's one thing you could list data from a flow. All right. I'll make a formal definition of it. So I give in some flow phi on a manifold. The periodic data of phi, okay, p phi, is just what I said. It's the set of free homotopy classes of loops. So what should that be? I should take an element of pi1, and I should record its free homotopy class. So this is really a conjugacy class in pi1. Okay. I'll write it like this. All right. And the way I set up orbit equivalence, it didn't really care what direction your flow was moving, just the foliation by orbits. So I shouldn't care about orientation, whether I'm moving in one direction or the other direction along this loop. So I'm going to say the collection of loops so that either this loop or its reverse direction is represented or is a periodic orbit. So let's make an observation. If I have an orbit equivalence between two flows, then it carries this data along, right? If, what did I call it? H, M to M is an orbit equivalence between, let's say, phi and psi. I'm dropping the t's here kind of lazily because I don't really care about time. Then H takes the periodic data of this one flow to the periodic data of the other, well, up to whatever it did to pi 1, right? Where this is the induced map on free homotopy classes. Right? You take some loops to some loops, you can write down what that does on the level of free homotopy classes of loops. Okay. So writing down this algebraic data, gives you an invariant of orbit equivalence. In particular, if you're trying to understand, orbit equivalences that are isotopic to the identity, right? Then this map is trivial. So this set is preserved. And the theorem that we proved is the converse of this for transitive Anosov flows, and actually for a more general counterpart that I decided not to get into the weeds with today, called pseudo-Anosov flows, that allows you for certain singularities in this behavior. So this was in two papers, actually, and you really do need two different approaches to this problem. And one of my goals today is to tell you where these two parts come into play. So the first is joint with Thomas Barthelme, and the second also with Stephen Frankel. And it says the following. Actually, let me state the easiest possible way to write this down first, where I make big simplifying assumptions so I can write fewer words, and then I'll remove them, and this will help us it be easier to parse. All right, so my first simplifying assumption is that the three-manifold doesn't have any embedded tori. That will make my life easier. So let's say it's like, I don't know, hyperbolic, meaning it invites, let's just say has no essential tori, another way to say that topologically. So there's no, in its fundamental group, there's no Z cross Z. That's a way you could think about it. And I have two Anosov flows. And at least one is transitive. Well, then the other one actually is going to be, actually, let me write down first. Okay. So the statement is that this invariant is now complete. The periodic data of one agrees with the periodic data of the other, if and only if they're orbit equivalent by, well, I've written down equal. So by some map H that doesn't do anything to pi1, isotopic to the identity. So the converse of this holds. And let me remove isotopic to the identity. What should I really say here? If it induces some, I don't know, big map H on, you know, pi1 up to conjugacy, then I should just put H here. All right, the other annoying assumption is we can remove some statement about the topology of your manifold. Okay, but at a cost, you need, in some very special cases, finitely much more data. All right, so I can take this and say arbitrary. Okay, but as well as orbit equivalence classes, since this is an intro talk, I will say that there is something which is actually kind of tricky to define that we call signs. Agree? Okay. So this is a finite collection of plus minuses that you can associate to certain pieces in the torus decomposition of your manifold. All right. So just to say in words, if you're an expert in three-manifold topology, if you look at the JSJ decomposition of your three-manifold, some pieces will be ciphered fibered. And on these, some of them might happen to have the direction of the fiber represented by a periodic orbit of the flow. In that case, weird stuff can happen. And in joint work with Barthelme and Sergio Fenley, we listed exactly what weird stuff can happen. All right. But there's a weird flip move you can do that preserves all the periodic orbits sometimes and changes the orbit equivalence class of the flow. Yikes. Okay, but there's only one weird thing you can do. And so it's really just like a plus or minus attached to did you do it or did you not? And that's what we label as the sign. If you're trying to understand this theory for the first time, you should ignore the orange part here and say that if your manifold is sort of topologically simple, then you have this as a complete invariant, just the periodic orbit data. Okay. Okay, so let me finish off our time here by telling you the tool for the proof and why this sort of breaks the proof into sort of two cases, which are philosophically very similar, but actually you have to kind of execute them separately. So what we're going to do is we're going to reduce the dimension of the space we're looking at the cost of changing a continuous dynamical system into something discrete, an action of a much more complicated group, but a discrete group. Why is this helpful? I mean, so I was talking, giving a talk on some of this work the other day, and a student in the audience said, like, just paused everything, was like, I'm struggling here. How do you visualize things in 3 dimensions? Like, how do you see what this flow looks like in a 3-manifold? And I was like, yes, like seeing 3 dimensions is hard, right? Like, I don't know if you ask Bill Thurston, he would have said, you have to imagine yourself inside the space moving around, or maybe you look on it from above. 3 dimensions is hard to see. 2 dimensions you can draw an accurate picture of. So we're going to reduce dimension. Right. And this tool was developed or used independently by Thierry Barbeau and Sergio Fenley starting around 1994 or 5-ish. and working both independently and then together, they've come up with this powerful framework for studying Anosov flows on three manifolds, and it's called the orbit space. All right. So what is this? Here's the setup. I have my flow on a manifold. Can start setting this up for any flow on any manifold. Okay. I can lift it to a flow on the universal cover. Okay, I just lift the generating vector field. Okay. It's still Anosov. My invariant distributions here list to an invariant distribution here. Everything's great if I started with something Anosov. All right. And then what I'm going to do is I'm going to collapse this down, quotient it by an equivalence relation. All right. So O phi, the orbit space, is by definition the universal cover of my manifold. Okay, mod out by, I take every orbit of this lifted flow and I collapse it to a point. So every point is equivalent to every other point in its orbit. Right. And the theorem, I'll credit both Barbeau and Finley for this, because they're both using this, which is that this orbit space is topologically a plane, homeomorphic to R2. No geometric structure, no metric structure, anything, but topologically it's a plane. Okay, but okay, so more than that though, I have some extra structure up here on my universal cover. The fundamental group of my manifold acts by deck transformations. My flow came from something downstairs, lifted up. So this action respects the orbits. It sends orbits to orbits. So that means I get an induced action on the quotient. So this comes with an action of the fundamental group of your manifold. It also comes with a pair of transverse foliations. So if you remember back to the definition of Anosov, I had expanded and contracted directions. If I think about the union of the expanded direction in the flow, it's a general fact, this is always tangent to a distribution. Sorry, this is an integrable distribution, always tangent to a foliation. So on this manifold with this Anosov flows, I have invariant, pi1 invariant foliations called Fs and Fu, the stable and unstable foliations, which is they're tangent to the direct sum of ES, S, and X, or EU, U, and X at every point, respectively. So these are two-dimensional foliations on my three-dimensional manifold. These all came from data downstairs on my compact manifold. So again, they're preserved by the action of the fundamental group. I can pass to this quotient, all right? And I get not just a plane, but a plane now with two transverse one-dimensional foliations. Okay, maybe I'll write not fancy F, S, and FU. Okay. And the action of the fundamental group on this plane preserves these two foliations. Oh, okay, the last part of this theorem that lets us really study flows from the orbit space perspective is due to Barbeau, following an argument of Gis. It says that if you understand this data, a plane, some foliations, an action of a discrete group, you understand the orbit equivalence class of the flow completely. It determines it, right? So to write this down precisely, what should I say? If I have two Anosov flows on a three-manifold, okay, then these are orbit equivalent. Sorry. Okay. Via some map H. Okay. If and only if their orbit spaces look the same, these are homeomorphic via some map, I don't know, F. That takes foliations on one to the foliations on the other. Put some subscript phi so we know what they are. The F, S, or U. I could swap them, but the pair goes to the pair. Okay. And conjugating the actions of the fundamental group. Okay, so when you write down this conjugate, or the fact that it's equivariant, you have to take into account what H is doing to the fundamental group. There might be some automorphism. If H here is isotopic to the identity, right, that's just saying that your conjugation is really literally what you think it should do. You know, F deck transformation, F inverse, whatever. That action is the action of the transformation, the element of the fundamental group on the other side. Okay. So what is the upshot of this machinery is if you want to classify Anosov flows, then all you have to do is understand actions of discrete groups on planes with foliations. Right. And that's what we do in this paper. We axiomatize dynamically what these things can look like. Right. The action of the fundamental group has some nice local properties. You'll see expansion contractions at points. Transitivity of a flow corresponds to a dense orbit for this discrete group. We write down what this is. We forget that there was even a flow in a picture, and we show what having the same free homotopy data looks like in this setting, and that this kind of information just translated to the orbit space gives you a complete invariant up to, you know, conjugacy of these actions. So that's the whole setup for this. Maybe I will conclude in my, last minute here, just draw you a picture of like what this could possibly look like. So the study, it's really kind of wild what these orbit spaces can look like. Right. Of course, you can have, what's a plane with two transverse foliations? I could take R2 with the usual vertical, horizontal foliations. That's a fine thing to put in my gallery of possible orbit spaces. There are examples where it looks like this. Okay. Not all examples, though. If you took your three-manifold to be the unit tangent bundle of a surface of negative curvature, our first example of Anosov flows, you don't see this picture where like every leaf of one foliation crosses every leaf of the other. Instead, you see a picture which topologically looks like this. So my plane won't be a patch anymore. It'll be like an infinite strip. And I take it like this. So you'll notice that each vertical leaf here has a kind of a supremum and infimum of horizontal leaves that cross it. Okay? And in general, you can have crazy things where you have sequences of leaves that accumulate onto unions of leaves. So it's not just like nicely listed in a row. You can have sort of non-Hausdorff behavior in the leaf space happening in both directions. Limits onto this. Right. So there's a very rich structure theory of what these can look like. It's surprising that you can reconstruct a homeomorphism between them that conjugates some group action. This is really a good, powerful invariant that lets you understand this. Okay, I think I have exhausted my time, so I will say thank you. I am happy to answer questions sometime in the future, but thanks.
Thank you, Katie. Okay, I know you have to run away from the room, so we don't have time for questions, but Maro's here, so maybe you do have to leave the room, right?
Yeah, I gotta leave soon. I will overstay my welcome. But also, I welcome any of you to like shoot me an email at some time, if that makes sense, and pose a question. I'll do my best.
Oh, yeah. So if you have questions for Katie, you should email her. If you're scared, you should email us and we will email Katie with the
Yeah, you could
questions.
collect a list.
Yes.
Yeah, that'd be
But
fun.
yeah, but you should not be scared of Katie. So, so thank you again. I'm gonna let you go, I think.